Okay, so we're recording. Off we go. So new section today. This will finish up chapter 5 for us, by the way. That's a little bit exciting. We're getting into chapter 6, in fact, today, hopefully. And chapter 6 is some new ideas, things that are different and really fascinating stuff. So anyway, that's a preview. But finishing 5.6 first. So we're going to start off by talking about something called the average value of a function. I'm going to start before that with talking about something called a weighted average. Now, y'all may have heard this term before. I hope you've heard this term before, specifically in our course syllabus. The way course averages are going to be computed in this course is as a weighted average. Right, so this is an important concept to make sure that you understand. And by the way, while I'm at it, let me just point out, if you are in any sense unclear about how grades are computed in this class, just come talk to me. I'll be happy to clarify. I think it's pretty straightforward when you see it, but there are some, some slightly confusing aspects. But anyway, just come talk to me. Be happy to clear it up. Okay, all right, so here's how averaging works. Here I'm averaging 6 numbers, and you'll notice that some of them are repeated. We've got 2 4s, right? We've got 3 8s. But 6 numbers, and you average them in, of course, the usual way. If you take this 6 and kind of spread it out like that, then you can kind of group together like this, which you rewrite like that, and likewise for the other numbers. And note that 2 appears twice. This 2 is telling you how many 4s you have, and this 2 is telling you how much of the 6 in the denominator comes from the fact that you had 2 4s. Right? So this is what we call a weight. This is that's a weight. It's the weight of 4 in this weighted average. And so, again, you can look and trace it back to where it came from. It's just a way of saying, how many times you're going to count that number. And having a weight of 2 means it's in a reasonable sense twice as important as this number 7 that has a weight of 1. Right? Okay. All right. So with this in mind, we generalize, and you'll notice that this looks a lot like that. Right? And the idea is that we've got all these weights for the various different things that we're averaging, and the numbers that we're averaging are what you multiply by the weight in the numerator, and then add up, and then then eventually divided by the total weight. So this is just a kind of a rewrite of the formula that we started by example. Okay, so this in general is called a weighted average. Now, this argument that I gave here, it kind of motivated by the idea that a number will show up a certain number of times, and it's sort of implicit then that means that the weights are integers. But if you think about it, in this formula here, there's no particular reason that weights need to be integers. Right? And so just think of the weight as, how much impact is it supposed to influence on the average that you're computing? So the weights do not have to be integers. Okay, so here's a scenario very closely connected to how grades are computed in this course. Not exactly the same, of course. You'll notice that the weights, though, for the 3 midterms, the weights are 20, 20, and 20, just like in our class. Difference being, of course, that for our final exam, the weight is only 30, not 40, right? And there's also homework and attendance, so a little bit different, but very similar to our class. So suppose this student, Bob, on the 4 relevant exams, Bob gets these numbers. What grade does Bob get in the class? Right? You see, Bob got a C on the first exam, then he started bringing things up, and how does this average? And the arithmetic is straight out of this formula. Right, so you'll notice we've got the weights, 20, 20, 20, and 40, right there, right? And then we've got the numbers to be averaged that are there, and there. I'm just straight up plugging into the formula. A bunch of arithmetic ensues, and out comes the average. Here we got 2.96 something, and What does that mean letter-wise? Well, that's a whole separate matter. The way I do it in this class is with the bins that I have, again, documented in the Sakai site. So all the information you need is that this would, in my class, this would round up to a B. Okay. All right. Okay, so that's called a weighted average. A lot of good things you can do with weighted averages. One of them is to define something called the average value of a function. The average value of a function is a weighted average. It's really what it is. It's a weighted average where you use size as the weights. And you can see that right here in this formula. And let's see, I'm going to do this so I can get it all on the page. This, I claim, is pretty naturally motivated by that formula that we've been working with. And literally, right, the sizes are the weights. So these weights here are how big are the little subintervals that you're chopping it up into. And of course, in the limit, that means the weights are the d-axis, right? And then the things that you're averaging here, we're averaging the values of a function. So we'll say the average value of a function. Well, then those are the v's from our original formula. And of course, integrals are just summations with a limit in there. But anyway, you can see how this is very strongly motivated by the formula we used there. Now, this does simplify, I suppose, a little bit. You can this integral of the weights down here is just b minus a. So that's nice, I suppose. And if you'd rather memorize this formula, then you can. I'll tell you what, though, I personally don't. I like to understand things from where they come from, and this integral is takes me about a third of a second, right, to remember how to compute this denominator. But the point is, I can connect this to the motivation for weighted average. So I like to think of it this way. You, of course, can suit yourself. Easy example. If you're interested in the values of sine x, right, you want to find the average value of sine x from 0 to pi. You plug in to the above formula, and the average value of sine x is 2 over pi. Okay. All right. You can do the same thing for multivariable domains. Same idea. Weighted average. All right? It's a weighted average where the size is the weight. Right? So again, it's the differentials in the limit. So of course, these are little differentials of area, not little differentials of width. Right? But morally equivalent formula. And of course, then we're adding up over the entire whole. Well, the way we add up over a two-dimensional region is with a double integral. So all the same motivations, just applied to a two-dimensional setting. And again, this denominator, I suppose, if you really want to, you can rewrite that, and it makes it ever so slightly more compact. But again, this one, I'm just going to make my pitch. This one connects very naturally to the general concept. And again, I think it's a better way to think about it. Okay, and again, example. Let's suppose we're looking at the function x squared, and I want to know its average value on the unit disk. And it's a kind of a weird question if you think about it, because, the unit disk is just kind of round sort of a shape, and there are some points where x squared is quite, pretty big, almost as big as 1. But there aren't very many of those points because the way the disk is shaped, there's just not a lot of points. There's not a lot of y values when x gets big like that. There's a lot more points where x is small, because then there's lots of y values. Right? So the fact that this is a question on the unit disk makes it a little bit weird. And it is resolved, of course, just by plugging into the formula, the area, of course, easy, old high school geometry. You got to crank out an integral. This integral is more easily done in polar coordinates. And recall that, of course, polar coordinates is a tool in your toolbox. And be on the lookout for when you might want to use that tool. Nothing about the statement of this question suggested, hey, by the way, use polar coordinates, right? But it's a good thing to be on the lookout for, and it saves us loads of trouble in this case. And again, compute. The answer, oddly, turns out unexpectedly to be a rational, simple fraction. What are the odds? You see the unit disk there, you're kind of thinking, oh, the answer's probably going to have a pi in it, right? You'd think. But, yeah. All right. Okay. Here's another application of weighted averages, and that's this thing called center of mass. There's different ways that you can think about center of mass. I'm going to start off, this being a math class, of giving you the point of view about weighted average. This is a very succinct, very crisp way to think about center of mass. It's a weighted average. It's a weighted average of position. Right? If you have mass at various different locations, the center of mass is just the weighted average of those locations themselves. Right? So we're going to average the x coordinates, as it were, in this case. With the weights, of course, being the masses. Right? So very simple way to think about it. Now, from a physics standpoint, and this is also a good thing to note, and it's not a physics class, but yeah, it's one of the big motivations for the class is to have applications to physics. So we're going to talk about a little physics in this class. But anyway, it's the balance point, right? It's where should you put your finger, right, to hold up the thing that you're talking about. And I'm not going to risk dropping my stylus here, but you know what I mean. So if you were to try to find the place where it balances, that is the same as the center of mass. And you can think about that from different points of view. One way to think about it is to think, well, this amount of mass applies a torque clockwise, and this little piece of mass is smaller, but it's further away. It applies a torque counterclockwise, right? And so the big idea to get it to balance, right? Balance means that the total torque is equal to 0. That there's just as much force pulling down one way as there is pulling down the other way. And if you write down those torques and set them equal, etc., then you'll get the exact same formula. So, okay. Alrighty. So now this picture, of course, is based on there being just two masses. But in general, same idea. Weighted average of position. Notice that position, then it goes right there. Okay. All right. Now, the weird thing about this integral, we haven't really seen an integral quite like this one before. Because the integrand is a vector. Right? Every integral that we've done in the past, we've, chop it up, add it up, and all that, double integrals, triple integrals, various different kinds of integrals, right? But the integrand has always been a scalar, like density, or something like that. Height, maybe, right? But we've never had a vector integrand before. So it's an eyebrow raiser. Hey, wait a minute, slow down. What is that? And now here's the good news, though, if you kind of think it through. What am I going to do with that vector? Well, I'm going to multiply it by a scalar. How do I multiply vectors times scalars? Well, one coordinate at a time, right? Now I'm going to be adding up a bunch of vectors, it seems. How do you add up vectors? Well, one coordinate at a time, right? So the beautiful thing about it is that everything that happens in this numerator happens one coordinate at a time. And so you can just do it literally one coordinate at a time. So that's really good news. It's really easy to deal with integrals where the integrand is a vector. There's not that much to it, really. Side note, a little bit of foreshadowing. Probably won't get to this today, but there is a different version of this where your integrand, in a way, is a vector, but in a different way than this, and that does make things get a little different, a little strange, and that's going to require much discussion. But that's a different thing. This is the simple version. Okay, so let's do this example here. Suppose we have the upper half disk. Right, here's our upper half disk. And let's suppose that there is mass uniformly distributed. Now, in particular, I'm going to make the density equal to 1. Just to, this is our first such example, so we'll keep it convenient. And let's see, I guess while I'm here, I'll notice the radius is A. Right? And so the question then is how to compute the location of the center of mass. Okay. All right. Here's the formula for the x-coordinate of the center of mass. And that's just straight out of the formula above. Right? That's that formula right there. First coordinate of the center of mass. Okay, and you can compute this integral by any of several different means. Again, I want to remind you, the best method will not always announce itself, right? Part of your job is to be on the lookout for, be constantly rooting around in your toolbox to find where is the best tool that I can use in this circumstance. And this one, we'll notice that the domain is symmetric over the y-axis. Oh, right? Eyebrow raiser. Possible awesomeness. The integrand. Well, and by the way, you got to think through then what's over that line. What is the formula for reflection? And I think you can see that what happens when you reflect is the x-coordinate's going to go negative. Well, that means that the integrand has the appropriate odd symmetry. So this integral is equal to 0 by symmetry. Boom. Done. Everybody good? So this is by the way, this is a flashbacks to my undergraduate physics major. I did this a bazillion times. Right? And again, outside of the context of Math 219, 0 by symmetry. And just, walk away and just keep on cruising. In this class, 2 seconds. In this class, though, you do have to supply the details. And remember the 5 things that have to be shown, and you've got to make sure to give me that complete argument. It's still worth it, though. I'd much rather write down those 5 details than have to go through a tedious integral. Yeah, question?
My question was like
that's so it's the same 5 that from last time. Yep. All right. Okay, so let's find the y-coordinate. Another thing real quick. There is a different case that could be made as to why this has to equal to 0. And this different case is what I would call a physics argument. Because you can sort of imagine from a physics point of view, if you literally had a physical example of this thing, and if you were holding it up with, with your arm or something like this, and you're balancing it on your arm, not hard to see that it's going to balance on the axis, right? Here's the thing. That's a physics argument. This is not a physics class. We may do some physics applications in this class, but I'm always going to want mathematical arguments because this is a math class, right? So don't say, it balances because of physics intuition. That's not an acceptable answer in this course. Okay. Alrighty, let's do the y-coordinate of the centroid. Side note, sorry, forgot to mention, the word centroid is sometimes an alternative to center of mass. Okay, so let's see, the y-coordinate. Here's the formula. Right, weighted average of the y-coordinate. And details to be done. Obviously, the area is an easy thing to write down. Excuse me. The question is how to compute this double integral, and here's your 2 options. You can do dx dy slicing or dy dx slicing, and it's another one of these circumstances where how do I know which one's going to be easier to evaluate? And sometimes the shape of the domain helps you with that, and not so much here. Right? Sometimes so for example, where the corners are, no help in this case. Or which variable is more easily a function of the other? No help in this case, right? Each one is a square root of something, right? So, this is an example, though, where I think once you write them both down, and maybe even if you can see it coming a little bit, but anyway, having written them both down, I have a strong preference in my mind for this one. And the reason why is because I'm kind of looking down the road just a little bit, and I see I'm going to do an antiderivative of y dy. That's going to give me y squared, right? Well, half, right? But that squared is going to kill this square root, and then there's no square roots left, and it's all downhill after that, right? So this is the kind of thing that you can kind of be on the lookout for. That's really nice. If you do this way, I mean, it's not that big a deal. You have to do a substitution. Not the worst thing in the world, right? But it's still, nevertheless, I think easier, a little bit easier to do it that way. So again, always be on the lookout for options, and always consider what's going to make your life easiest. Okay, what do you think? Everybody with me? All right. Okay, so here's another physics concept, moment of inertia, that turns out is very conveniently helped with some math, and in particular Riemann sums. There's something I think a little unusual about this example, and that is that most physics examples we do, we start off with a physics concept. I want to compute mass. I want to compute work, something like that, right? The thing I want to compute comes first, and then the math is just the tool that we use to compute it. That's actually not what's going to happen here. What I'm going to do, the way we come up with the idea of moment of inertia, is we compute something different. We're going to start off by computing kinetic energy. And along the way, while computing kinetic energy, we're going to find ourselves having effectively kind of discovered a different physics concept that's very useful on its own. And it's going to come up unexpectedly. And I think that's kind of neato. And this is a real thing. This happens a lot in doing science. That you're interested in one thing, and then you kind of run across, hey, I apparently need to be interested in this other thing. Okay, so here's the scenario. We're going to consider rotating motion. So we have an axis, and we have something that is rotating around that axis. Okay. So everybody remembers this formula, I hope, that the arc length formula, how it relates to angle and radius, old high school geometry formula. And I'm going to very innocently just take a derivative of both sides of that equation. Radius doesn't change, of course, it's just rotating. Taking a quick derivative, what we have now then, this is a different relationship, but it's a relationship between what you might call speed, namely how fast is your actual position changing, right? And this thing here, the rate of change, not of position, but the rate of change of angle. So we call this angular speed because it's kind of like speed. It's a rate of change of something that kind of describes where you are. If you think about it, theta tells you kind of where you are in a way, but it tells you as an angle. Right? So the rate of change of this thing that kind of describes your location, you see the motivation for the word speed there, but it's an angular version of speed. So that's the term angular speed. And just a heads up, there is a more, I'm going to say actually a more common term for this is angular velocity, and it's just a little bit uncomfortable for me because a velocity is supposed to be a vector. This is not. This is a scalar. So this is really more analogous to speed than velocity. Anyway, heads up, you're going to hear people say angular velocity. They mean angular speed. Okay, so let's talk about kinetic energy. How would you write down the formula for kinetic energy if you had just a little piece of mass particle of mass, it'd be no problem. A little bit of algebra. But what if you have a large blob of mass that's rotating around, right? And you want to know then what is the kinetic energy of this large blob? And can you just write down 1/2 mv squared? And I claim you can't, because if you think about it, as this thing rotates around, that little piece of mass closer to the axis isn't really moving very fast. Pieces of mass that are further out away from the axis, they're moving fast. They make a much larger circle in exactly the same amount of time as the other pieces over there. So the problem is, I can't use this formula because there is no well-defined velocity, speed, I should say, that I can use. Does everybody see the problem? Right. So what to do? As is very often the case, when you find yourself wanting to add up a thing, but that thing is awkwardly defined on a large region, chop it up, add it up. Right? This is what we do in calculus classes. We take problems over large regions, we chop them up into little bitty pieces, and then on each little piece, we hope maybe the problem is simpler. And then we just add them up. So that's the strategy here. And so if I look at little pieces, here's how you do it. Grand total kinetic energy, chop it up into little pieces and add up the amount of kinetic energy on each little piece. On each little piece, it's no big deal. On each little piece, 1/2 mv squared, where v represents the speed of that little piece, which is perfectly well defined because we're looking at little bitty pieces that are just not large enough for there to be any. I mean, you got to worry about limits and stuff, right? But on little pieces, every part of that little piece is pretty much going the same speed. And then, you got to rewrite things a little bit. Keep in mind from above, we've established that v is r omega. That was that right there. Keep in mind that omega is a constant. All right, so as this thing rotates around, there are different pieces that are moving at different linear speeds, but the angular speed, and therefore omega squared, is a constant that you can just factor right out, like so. Yeah, question.
With the example you just used,
Uh-huh.
the speed changing with the distance, like the radius?
Oh, absolutely. So this speed depends. This is a function of where you are. Right, so this is effectively what is going to end up being our integrand, and our integral is wrapped up inside of here. You're right, this is not a constant over the entire solid,
Right.
but it is constant on each little piece.
Okay, so why do you do dm and not dr?
Because keep in mind we're computing here kinetic energy, and kinetic energy is 1/2 mv squared, and on any given little piece, the mass of that little piece is what we call dm. Is that cool? So we got 1/2 the mass is dm, representing the mass of that little differential piece, and then the speed is at that location, wherever that little piece of mass is, there's some speed, and you're quite right. It will depend on position, and we'll see that develop. Yeah. Okay. So move things around, blah blah. The 1/2 factors out, etc. And so you get down to this, at which point I'm going to do a move that will make more sense in a second. I'm going to take this thing here, integral r squared dm. I'm going to give it a name. I'm going to call it I. And just bear with me. Having rewritten that thing as I, notice that my formula for kinetic energy, rotating kinetic energy, all of a sudden looks shockingly analogous to the old formula for linear kinetic energy. It's like, oh my gosh, it's the same structure. It's 1/2 something times something squared. And then further notice, the thing that I'm squaring, that in the linear case is linear speed, well, in the angular case, it's angular speed. So the structures are similar. The role that this is playing is it's really playing the angular version of speed. And so that strongly suggests that this thing that I've called I must be an angular version of whatever that is. Mass. Okay, so this thing here, this thing called I, this integral that I just kind of lumped into a single name, apparently in an angular context is playing a role kind of like mass. So that's what we call it. It's an angular analog of mass, in the same sense that omega is an angular analog of speed. So that's the motivation. And with that in mind, there's a lot of syllables in here, and I think it's slightly fewer to call it moment of inertia. The reason that they call it moment of inertia, I think, is largely historical. It's a pretty clunky term, really. Think about it, right? I'd be pretty happy with angular mass, but I'm not going to fight that that battle. It's classically called moment of inertia. So this is what it is. And as noted, we weren't interested in that thing when this whole thing started. We were interested in kinetic energy. We were computing kinetic energy. And along the way, hey, check it out. This expression here, really natural to think of in a different way. Okay, so that's a little physics background. The punchline is you need to know this formula. It's called moment of inertia. This is the way I like to understand it. Integral r squared dm. We'll talk in a minute about what r is. I'll just remind you real quick up here, though. R represents the distance from wherever you are to the axis of rotation, right? So R represents distance to that axis of rotation. We'll see some examples in a minute. Okay. dm, now, that again represents the amount of mass in a little piece of our domain. That's density times volume, and I could have rewritten this as density times dV. But the thing is, sometimes you have a two-dimensional lamina of mass that's rotating, in which case dm is density times dA. And rather than have different versions of the formula to be applied in different circumstances, and therefore more formulas that you have to remember, I like to think of it as just this one thing, and then interpret dm as appropriate. dm is density times size, appropriate to the context. But just dm is all you have to think of. So this expression, integral r squared dm, always works, yeah.
So if you have like a point mass, it would be a single integral?
Yeah, well, no, if you have a point mass, then it would be not an integral at all. It's just a single point, right? So what you're thinking of is a zero-dimensional example. If you wanted it to be a one-dimensional integral, then you'd have to have imagine like if you had a rod of mass that was attached to a string and you're swinging the rod around, then it'd be a one-dimensional integral. Yep. Okay, so what is R? It always depends on the situation. It depends specifically on the axis of rotation, right? So if your axis is there, or if your axis is there, or if your axis is here, or whatever your axis is, right? R represents the distance from wherever you might happen to, whichever piece of your domain you're looking at, right? Your location and your integral. R is the distance. And notice it's different in every picture. Right? You got all these different possible axes you can rotate around, and there's going to be a different formula in each picture appropriate to the context. Now, some of those will be easier to remember than others, I suppose. But don't try to memorize just a single formula, which of course obviously wouldn't work. But also, please don't try to memorize a list of cases, because any list you make is going to be incomplete unless you memorize all infinite number of cases, right? Which you can't. So please understand the idea that r is the distance, and then make sense out of it in context. And so here's some examples that you can work from by analogy. Usually it's a pretty easy thing. If your axis is the z-axis, well, the distance to the z-axis, that's a horizontal distance. You can write down exactly where that point is, and boom. That's nothing. Finding the formula for r is not a hard geometry problem most of the time. So better to understand the concept than to memorize a bunch of formulas. Okay. All right, so an example, let's compute the moment of inertia of this thing. And let's see, our thing is, we need y to be between 0 and sine x, where x is between 0 and pi, and so that's this thing right here. Yeah? And notice now here we have a non-constant density. Oops. Right, so that's going to play in. Question is to find the moment of inertia around the x-axis. So there's our axis that we're rotating around. So when I do my integral, and when I'm looking at little pieces of my domain, what is the distance to the x-axis? The distance to the x-axis is that right there, which I think you can see from the geometry is just the y-coordinate of whatever that green point is. Is everybody happy? All right, so here's our general formula: integral r squared dm. Let's think about it for a second. We're in a two-dimensional context, so mass is density times area in this case. That's the context, right? So that took us all of 2 seconds to figure out. R we just discussed. R is y. Right? The density was given 2 plus cosine x. And then the region, we do have to, slice and dice the region here, and so that's gonna, you gotta think about which way you want to slice it. Again, I have a strong preference for slicing in this order because it's much more natural to think of y as a function of x than to think of x as a function of y. You'd be looking at arc sines, and nobody wants to do that. Okay. And then, compute. What do you think? Everybody okay? All right. Okay, we're done with chapter 5. Moving along now to chapter 6. So new kind of integral that we're going to have to develop here. The idea is not a hard concept, but it is different. And it is a sort of, we have to kind of wake up and reconceive of, remind ourselves, go all the way back to the fundamentals. Wait a minute, what are we really doing here? And here's the weird thing. So far, every domain that we've dealt with has been the same dimension as the space that it lives in. Right? So we've talked about, for example, if we're in 2 dimensions, what if we have a 2-dimensional region inside of R2? Right? And we've talked about if we're in 3 dimensions, what if we have a 3-dimensional solid? Well, 3-dimensional solid living in a 3-dimensional world. 2-dimensional area living in a 2-dimensional world. Those numbers have always matched up. They don't have to, right? We could totally imagine, what if I had, for example, a 1-dimensional curve, right, like this, and maybe I want to, chop it up, add it up, right? I want to compute the amount of mass on this curve, or what have you, right? But that's a 1-dimensional curve that's living in a 2-dimensional world. I can't use a double integral on this because there's no areas, right? This is a 1-dimensional curve. So double integral, not going to do it, not going to work. And the thing is, though, I mean, it's tempting to say, oh, it's a one-dimensional domain. Use a single variable integral. What's the big deal? It's a single variable integral. I didn't see any domains like this in Calc 1, right? Those are all one-dimensional intervals in the number line, right? One-dimensional intervals in one-dimensional worlds. This is a kind of a question we've never seen before. It's a brand new kind of a chop it up, add it up scenario. And so in the same way that when we started talking about double integrals, we had to write down a new notion of a Riemann sum. And then we started talking about adding up over solids. We had to write down a brand new kind of Riemann sum, right? Triple integral. Well, here we are. We have another new scenario. And we're just going to have to write down a whole new kind of an integral. And here's what I propose. Right, and this is motivated by the idea of, let's suppose we're interested in computing mass. I call it Q just to be general. But suppose you're interested in computing mass, and so there's maybe this is a bent wire. But it's more dense over here for some reason, and it's kind of less dense over there, and maybe more dense over here. You can't just multiply mass per unit length times length because, well, the mass per unit length is different as you move along, right? So, well, what I can do, though, is chop it up into little pieces and say grand total, the mass on this whole thing is the sum of the masses on the little pieces. Right? This is an accumulating quantity. Mass still is an accumulating quantity. And then furthermore, on each little piece, how much mass is there on that piece? Well, on that piece, I'm going to say that there is an appropriate notion of density. In this case, it would be mass per unit length. Mass per unit length, multiply by length, and that'll tell you how much mass there is in that little piece. And then I add up over the entire curve. Everybody with me so far? It's just chop it up, add it up. And then, the beautiful thing about chop it up, add it up is it turns hard problems into easy problems, because on this little piece, mass per unit length is pretty much constant. And there's a little length, and it's teeny tiny, and multiply mass per unit length times length to get mass. It's just very straightforward. Okay, so let's talk about notation. Now, again, I emphasize this is a brand new thing. We're just now defining this. So we get to choose what notation to use. And we're going to make up a notation. It's a new notation. But it's motivated by old notation, and I think you'd find it pretty natural to rewrite the differential as a D, right? And to, we'll just kind of recopy whatever that function is, whatever that density in our motivating example is, we'll just write that in there. And then a limit of a summation, integral. That's what all integrals are, is limits of summations. And this is a summation that happens over a single index, right? If you wanted to keep track of which piece you're looking at, this is number 1, 2, 3, 4, 5, 6, right? You only need one index to describe where you are. So single index and thus a single integral symbol. Yeah, question?
Are we going to do this with like a surface that's in the cube?
Yeah, totally. That's a great question. Yes, we are absolutely going to talk about other sort of dimensionally misplaced domains. Absolutely. But that's going to be a little bit later on. But very similarly motivated. Chop it up, add it up, look at my little pieces, etc. Yeah. Totally. Okay, so there we go. This is our notation. This is called a scalar line integral. A lot of people will just kind of casually call it a line integral, which is fine. It is a line integral. The only reason that this prefix scalar I think really ought to be in there is because as it turns out, and it's hard to see this coming, but this can turn out there's a different kind of line integral as well. There's actually two different kinds of line integrals that have certain things in common, but they're also significantly different critters. And as such, given that they are in fact different, there are important differences between them. I think it's appropriate for them to have different names. So I encourage you to think of this in your mind: scalar line integral, and I'm going to not divulge just yet what the other one is. We'll see it pretty soon. Possibly, probably not today, but very soon. One of the first things on Friday, we'll see the other kind of line integral. Okay. All right. Now, here's the nasty problem. Recall when we first wrote down double integrals. It was all pie in the sky and no clear, obvious, wait a minute, how am I going to compute this? Am I going to have to actually crank out Riemann sums here? Yikes. Right? And then turns out that there was a clever way that we could compute double integrals with iterated integrals and all downhill from there. Okay, so here we are again. We've got this brand new thing. Oh my gosh, am I going to have to actually compute this with Riemann sums? Say it ain't so. And good news, there is a way to compute this easily also. It's a little bit different. In fact, it's something that's highly analogous to change of variables, which we've done before. And the point of view I want to give you is, if you think about it, what was the purpose of change of variables? I don't like these domains. They're undesirable. We have bad domains. I want to change my integral on a bad domain to a better domain. Right? So with the same idea in mind, here I've got a bad domain. Bad domain. I mean, it's bad for different reasons. I mean, the bad domains we saw with change of variables were bad because corners and equations of curves that were weird, or just undesirable slicing process. This is bad because it's dimensionally unprecedented. We've just never seen something like this before, right? So different kind of bad, but still bad. And remember, the way you do change of variables, the big concept is to view your bad domain. Find some way to view it as being the image of something. If you can view it as being the image of something, then you can do what we call, again, the pullback. Right? The pullback is the act of plugging in. Everywhere I see an X, for example, there's this point here has an X coordinate. Everywhere I see an X, let's just recognize, all right, well, that's some function of t. And just plugging in the change of variables function. So view your domain as an image, plug in, aka pullback, and then just don't forget that while you're doing that pullback, one of the things you're going to have to pull back is your differential. Right? So we've got this ds here. How am I going to pull that back? Right? How do I write ds size over here? How do I write that in terms of t's? And convenient formula already exists. Distance equals speed times time. Right? This is old news. In fact, we wrote this down when we were doing arc length computations back in chapter 3. Right? So old news happens to be exactly what we need. ds, the thing that I need to pull back here, is a multiplicative factor times dt, my pullback differential. And so I have a pre-existing, I didn't even notice it at the time, right? As we were writing down these formulas, we didn't realize this was going to be a stretching factor. But it is. There it is. So, don't forget your stretching factor. Yeah.
I'm having trouble knowing, or how do you see that this is a bad domain?
Oh, yeah, because how else are you going to compute an integral on this? You can't, it's not a double integral, right? Because there's no areas. It's also not really a single variable integral. What are you going to do? Compute an integral from A to B? Look at the x coordinates? Because this doesn't take into account the fact that this curve is, it wiggles around and stuff, right?
You couldn't just do the vectors, your lower bound be like x of a, and then x of b is your upper bound, and then just have like if you had said that you could integrate
Yeah.
a vector just like coordinate by coordinate, so why can't we do that? Yeah.
I guess I'm not really entirely understanding. Oh, because we're not integrating location. I'm not integrating my position x.
Right.
I'm not doing an integral of x dt. Or if I were doing an integral of x dt or something like that, then yeah, sure, no problem.
Okay.
Right? But we're doing an integral of some function of x times ds. My differential, see that what you were talking about before was an integral that was defined on a single interval. Right? It was or defined on a domain that we liked for whatever reason. And here I've got an integral that's defined on a fundamentally different kind of domain. Yeah. Yeah. That's it's a little bit of a weird circumstance. Yeah. Okay, so we've got ourselves a formula. And let's see, how are we doing on time? Oh, and we're out of time. So there's a pretty good stopping point. I'll just note that we're going to, on Friday, start with a bunch of examples before we go on. All right, y'all have a good one. See you later. Oh, and of course, as usual, if you came in after I finished attendance, then stick around for